Dear students, myself Dr. Horish Kumar, for your course instructor for BPT-401. Dear students, as you know, the response of a material to the external magnetic field is generally the course of study of magnetism. On the basis of this response, magnetism is broadly categorized in three categories, mainly known as diamagnetism, paramagnetism, and ferromagnetism. Other subclass exists like ferrimagnetism, superparamagnetism, but main classes remains diamagnetism, paramagnetism, and ferromagnetism. To quantify the response of material to the external magnetic field, we define two quantities: magnetic susceptibility and permeability. Magnetic susceptibility is defined by radiation and rate equal to magnetic susceptibility, which is the ratio of magnetization to the field of intensity of the field. Magnetization is defined as the magnetic moment per unit volume. So we have V equal to mu h. This quantity is called permeability. So known as susceptibility. Again, we define the relative permeability. Relative permeability, where mu naught is the permeability of free space. Now, the diamagnetic materials are characterized by the negative and small susceptibility. Permeability is generally less than 1. Let me list the few materials which exhibit this diamagnetism. Rare gases like neon, polyatomic gases, N2, CO2, some covalent solid like carbon, silicon, etc. Few ionic solids, for example, NaCl, superconductor. To have an idea of magnitude of susceptibility of diamagnetic materials, let us allow me to write few examples. Susceptibility of this one is 1.3. This is negative value, 10 to the power minus 5. Susceptibility of methane is 3.1 with negative sign, 10 to the power minus 5. Susceptibility of helium is 1.6, negative 1.6, 10 to the power minus 5. Sorry. So, the magnitude of susceptibility normally remains with the power 10 to the power minus 5 or 10 to the power minus 6. The values are negative. Most of the times it is 10 to the power minus 6. Similarly, the relative permeability is less than 1. For example, relative permeability of germanium is 0.99993. So, susceptibility is generally of 10 to the power minus 6 order, and permeability is less than 1. One thing is to be noted that normally diamagnetism is exhibited by the atoms or molecules which have a closed cell structure. That is, cells are filled. Now, today I am going to discuss the classical theory of diamagnetism, which is also known as Langevin theory of diamagnetism, which is capable of giving an expression which involved the susceptibility with negative sign, and susceptibility is related with parameters like mass of the electron, average radius of orbit, magnetic moment of revolving electron, etc. To research an expression, let us first discuss atomic currents. What are atomic currents? In an atom, electrons revolves in a circular path. This circular path of electrons, which is very tiny, is equivalent to a tiny current loop, and this current loop is equivalent to a magnetic dipole. Obviously, it has a dipole moment and field. This field is very similar to the field of a tiny real magnet. So let us discuss how the things looks. So it is the orbit of an electron. Electron is moving in a plane orbit. Magnetic field of this loop is shown here. So the magnetic field is equivalent to the magnetic field of this dipole, magnetic dipole. So, which is a magnet. One pole is here, another pole is here. So it is a dipole. If the size of this dipole is reduced, then actually this can resemble to the field of this atomic dipole. So the magnetic moment is like this. If electron is circulating anti-clockwise direction, and if the orbit of plane of the orbit is xy plane, it is like this. Since the electron is moving with certain velocity, the angular momentum is also associated with this, which is opposite of this angle. Now this associated angular momentum can be calculated, which is nothing else I into A, where I is the current in the loop, A is the area of the loop. That is area of the atomic loop, which is nothing else by R square. Pi R square is the area. V is the velocity equal to EV 2 pi r square is equal to half EV r. Since the charge on electron is negative, this ML in vector form can be written as half E V R k cap if k is along this direction. K is perpendicular to the plane of the orbit. Suppose it is z direction. So, for future reference, let us write this angle of EVR k cap. This is the situation. ML is direction, vector L is along this side, along the eye. Now to discuss the diamagnetism, let us consider two electrons which are circulating oppositely. That is, their direction of motion is opposite. Before going into detailed calculation, let us discuss what is the effect of magnetic field on the current carrying loop, or on the loop in which electron is revolving, or the orbital in which electron is revolving. We have the potential energy of this dipole moment, Ml. Is ml dot V minus ml dot. That is the minimum of potential energy is along the field. That is in theta equal to 0 direction. This direction is the direction of magnetic moment. This is the direction of field. Theta is angle between these two vectors. Also, we have this magnetic moment minus half EVRK. Since the electron is revolving in a circle, it also having angular momentum, and this angular momentum can be associated with this magnetic moment. Let us see how. L is nothing else because it is moving in circle, that is electron is moving in circle, and VR, M is the mass of the electron, V is the velocity r is the radius of the orbit. So if you write ml like this, EVR, so multiply by m, divide by m, EVM, EVR m over m, K cap is equal to minus P by 2n. Okay. So NL can be associated with a vector L. Now, if we put this dipole in a magnetic field, the torque associated is given, or already have been calculated, is given by Z is equal to ml cross T. Let us write it like this. Since there is a torque, if this ml is somehow connected with angular momentum, or there is an angular momentum associated with this ml, then obviously it will not have the tendency to align with the magnetic field. For example, to consider the case of electric dipole, if you put an electric field, there is no, already you know that there is no angular momentum associated with dipole, electric dipole. So if you put it into magnetic field, there may be torque which try to align the field, the dipole, electric dipole along the field, which is the basically which is the origin of orientational polarizability. But here the situation is different. We have a angular momentum which is associated with ml. So we can write the torque as dl over dt is equal to ml cos b. And with the help of this relation, you can write this so clearly now the vector ml is not being aligned along the field. However, it is processing about the B. with a frequency called Larmor frequency, and this precession is called Larmor precession. The frequency of this precession can be associated with the magnetic field and can be written as gamma into V so the effect of this magnetic field on ML is such that it rotates about B, keeping this angle theta as constant. So the vector ML presses about B. Since the vector ML is perpendicular to the plane of orbit, so orbit will not remain stationary. It will rotate like this. So not only the vector ML, we also say that this orbit presses around B. This terminology is generally used, orbit presses. So let us see how this ML can be obtained. How this Larmor frequency can be obtained, and what is the effect of this precession on the electronic motion. We have this type of relation. This is nothing else gamma ML into V. ML has the component I MLX plus J MLY plus K cap MLZ. B is along Z axis. Okay. B is the magnitude. So if you cross multiply, you have I cross K, B plus J cross K, B, and I, J cap, K cap. Obviously, I K cross K is equal to minus J cap B plus J cross K equal to I. I cap right here MLX. Here this term MLY B we have this cross product. So if you compare the components from this side, you have this MLX, ML, M dot, MLX dot is equal to ML gamma ML by 3. Similarly, we have ML y dot is equal to minus gamma MLX v m dot lz is 0. If you solve the equations, you have MLX is equal to sin theta or omega sin theta MLX is equal to cos theta and omega is equal to gamma p. This is the solution of this differential equation. MLX, MLY, MLX, and where omega L, which is Larmor frequency, is gamma into V. So, this ML rotates with the frequency gamma into V. What is the effect of this precession on the electronic motion in orbit? The effect is what? If we consider two oppositely moving electrons, one electron will speed up, another will slows down. That is, one slows down and another is speed up. Let us see how it happens. output magnetic field is perpendicular to the plane of the orbit. So, before we have applied the magnetic field, the electrostatic interaction between electron and nucleus provides the centripetal force. So, this equation of motion can be written like this. Where r is the radius of the orbit, and this is exactly balanced by this centripetal force. Consider the electron is moving anti-clockwise direction, magnetic field is perpendicular to this. So, if we apply magnetic field, then there is a force on electron given by Fm where Q is any charge. For electron it is minus E. So V cross B. So this force is always perpendicular to the velocity d and magnetic field B, that is to the plane of perpendicular to the plane of B, V cross B. So this situation is like this: plane, magnetic field, electron is moving along this, B is perpendicular to this. So obviously if charge is positive, force is outward. But the electron has negative charge, this makes this force towards the center. So in case of electron it is minus E, V, VV. We write like this, magnitude wise, this direction is shown here. So we can write now the equation of motion like this: 1 upon 4 pi epsilon Z square R square plus E. Now where V dash is the new velocity in the presence of magnetic field, because now the equation is not the same. This equation is not same to this equation. Obviously the velocity will be different. It may be the radius as well, but Larmor has shown that, as I have already discussed, that the radius or the orbit remains same. Orbit remains same. What is going to change is the velocity of the electron, which reflect in term of Larmor frequency or correspondingly velocity. We have situation this. If subtract these two equations, we will get EV dash equal to M over R V dash square minus V square delta V minus B dash is a small quantity, generally small. let it is represented as delta V. Since B dash is slightly different than V, we can take these two velocities as equal. So finally we have EV equal to m over r 2 delta V. Or delta V equal to EVR over 2m. This is the change in velocity of moving electron. We can convert into frequency using E equal to R omega relation. And that change in frequency is the Larmor frequency. Now, if you consider this situation, here both forces are opposite. If you write the equation, then in case of positive sign, you have a negative sign in term EBV. So we get a change delta V in this equation minus EV R over 2. Identical. This change in velocity or equivalently change in frequency can also be achieved using a different concept, which is classical concept obviously, according to which if we switch on the field, there is a change in flux, and this change in flux gives rise to induced EMF. Induced EMF leads to an electric field, and this electric field works on the charge and supplies energy to it. Let us read this result using this concept. Suppose B initially magnetic field is 0. We switch on the magnetic field, so we have a change in flux. So E is minus d phi over dt. Induced EMF. This induced EMF is the line integral of this loop over this loop of electric field. Line integral of electric field over this loop is equal to E into 2 pi r, where r is the radius of this loop. So obviously E magnitude pi, E over 2 pi r. Now you have E over this, and E is again it d phi over dt. Now equation of motion of moving charge, that is electron, is m dv over dt is equal to E. So m dv over dt is equal to E And we have this relation. Let's change it to d5 over dt. Implies m dv equal to delta 5. The change in flux is dA there is the area of the object. So change in velocity is E over 2 pi r m into d pi r square. Which is EBR over 2m, which is same. So at this we can reach this result in another way. Now we have a change in velocity and we have the magnetic moment of EBR theta. Obviously, a change in V will result a change in ML. So, let us calculate this change for electron moving clockwise. This is half E delta V R K cap equal to minus half E delta V is E B R over 2m, where m is the electronic mass. Okay. This is minus 1 upon 4 E square R square B is this. This is the change in energy. When we place a atom, that is diamagnetic atom, in a magnetic field, there is a change in magnetic movement of an electron, and this is given by this. Where the electron is moving, anti-clockwise. This is clock. Now, if you calculate the change in magnetic field, change in magnetic moment in case of electron moving clockwise direction, the expression for ML, if electron is moving in a clockwise direction, so obviously now for the orbit, in which electron is moving along clockwise direction, the magnetic moment is, if electron is moving clockwise direction, the current direction is opposite to this, and then the magnetic moment will be along the field. So, for such a situation, ML is plus half EVR K cap. And now change is negative. So again, we have change due to this negative sign, 4m E square R square d K cap. In both the situations, with either electron is moving clockwise or anti-clockwise, we have change in angle, that is in magnetic moment, is opposite to the magnetic field. So when we apply the magnetic field to a diamagnetic atom, we have induced effect, and induced effect, which is in term of magnetic moment, opposes the magnetic field. So diamagnetism exists in most of the materials because it is induced effect. It will arise in most of the atoms, but it is masked by other effects. But in some materials which have even number of electrons, it is pronounced easily. You can notice. Now changing suppose we have n number of orbit, that is n number of electron in the atom, then the change delta m, it will be like this, 4 E square sigma that cycle will be like this. What we have done, we have taken the magnetic field perpendicular to the orbit. But in atom, it may not be the situation. In generally magnetic field and magnetic moment must have an angle. These two vectors must have an angle, may have an angle. So if theta is the angle for particular orbit, which is denoted as the ith orbit, radius projection of this, suppose it is xy plane, this is z, z. Or this is the projection over xy plane, that is this plane is perpendicular to z axis is perpendicular to this plane. So the projection of this plane is this, the radius of which will be, this is the angle, this is direction of B, this is ML, this is 90 minus theta, this is 90 minus theta, and if we draw perpendicular, this is 90 minus theta means theta. For ith orbit it is theta I. Yes. So radius of this projected circle is Ri cos theta. So we, in general situation, we must replace this Ri by this Ri cos theta. Cos theta is. Suppose a specimen of material consists of an atom or molecule and volume is unity. Then this M corresponds to magnetization vector. M is for N but in a specimen atoms may be randomly oriented, so we must take an average of this Ri cos theta. That is, it must be replaced by an average value. With average is where average is taken over all possible orientations. If suppose the coordinate of this point are x, y, z or xi, yi, zi. So obviously we have this type of relation. And because this is z axis and this is r cos theta I, we have Ri cos theta I square is equal to xi square plus by I square. This is the radius of this circle. Now, suppose atom is spherical symmetric, then the average value of xi average value of yi square all are equal and are equal to 1 upon 3 Ri square, the average radius of the orbit. You may take it as the radius of atom. So we have, for this, we have Ri square cos square theta I is equal to 2 by 3 R square. R is average value of R square. So let us put this relation for average value. We have m is equal to minus 1 upon 4 e square b n m 2 by 3 into n, because n summation is over n, so average value, the summation is equal to average value into n. If you have z atoms, z electrons, then you may replace it and may replace this n by z. Six. We have V equal to mu h, because magnetic field is applied in terms of h generally. So let us change to h. Also magnetic susceptibility can easily calculated with the help of an expression which involves m and h. Also, in case of diamagnetism, mu is almost equal to mu naught, slightly less than mu naught. So let us put it here, equal to minus m equal to this e square b n 6m and v equal to mu h. So let us replace this by h0 and this r square. The expression for magnetic susceptibility m over h is equal to minus e n mu naught 6. This is the final expression which the Langevin has obtained using classical approach. Here we have the missed n. So let us write n. Final expression then will look like minus mu naught E square section n